All right, how's it going, everybody? I am here on Friday, April 9th, making this video here today. Today we're going to be getting into our week 12 topics here. We're going to look at sections 9.1 and 9.2 this week. In general, our upcoming next topics are our first three sections of chapter 9 here. We're going to talk polar coordinates, polar equations, and graphs. Those are our two topics this week. Then next week we're going to see how those relate to the complex plane, and we're going to use something called de Moivre's theorem. It's not a de Moivre right there, de Moivre's theorem, to talk about how we can kind of understand how to do some math with some complex numbers and recognize that when we're talking about complex numbers, I think that some of us are vaguely familiar with the concept of um, attempting to do math beyond just getting stuck when we see things like the square root of -1. Hopefully, one of the things that you guys know from algebra is that it doesn't make any sense to take square roots of negatives, but that's only true if we're expecting to get out a real valued number. There is no sort of standard number that we can understand what we're going to get out from the square root of -1, but that doesn't mean it's not a useful quantity for us to do some math with. So that's what we're going to take a look at with our complex plane. Complex or imaginary numbers, both really, really bad names for those numbers. They're not complex, they're not imaginary. But those are the names that I'm assuming that you guys have heard attached to those things. So that's what we'll be talking about a little bit in section 9.3 there. So let's go ahead and get started. So the good news is that I think that this week is one of those weeks where the topic that we're covering certainly has a lot of depth associated with it to where it can get to be a very complicated topic. We're not going to go to any extreme depths with this. So this is one of those things where we're going to, in a sense, create a new measurement system. So that's a little bit weird, but it's going to turn out to be more beneficial to us than a challenge, I think. And so this is one of those weeks where I hope that you find this stuff to be relatively easy. It is sort of like a brand new idea rather than stuff that you're already familiar with. But that just means that we're sort of covering sort of the introductory concepts associated with it. So hopefully, as long as you're able to sort of open your mind to doing measurement a little bit differently than you're used to, you'll find this to be not too terribly difficult here. So let's go ahead and hit it. So in section 9.1, what we'd like to do is we'd like to introduce this concept of polar coordinates. And this is going to be a new way for us to identify where certain locations are at in the plane, and therefore it's a new way for us to identify different equations of graphs. What we're all really, really used to are called Cartesian coordinates or rectangular coordinates. Say that here, rectangular is another reference for the coordinate system that we always use. And in our Cartesian or rectangular coordinate system, we define our location by our horizontal and our vertical distance from some central location, the origin, right? So if you go to graph where you are on any given graph, if we're trying to describe a location, if we're sitting out here, somewhere out here in space right here, we call this x comma y, and what you guys know is that that means that we went x units to the right from 0, 0, and y units up from 0, 0. So we can sort of picture like this dotted line. That's sort of like your two-step process there. We went x units right and y units up. We refer to this, therefore, as rectangular coordinate systems because any sort of like path that you take is always on this rectangular grid, right? I don't really envision myself ever moving diagonally when we're in our typical XY coordinate system right there. X describes only left, right. Y describes only up, down. We're going to modify that a little bit today. So, for example, why do we kind of like our rectangular coordinate system? It's really good for some settings. So, for example, what do all the points on this line have in common with one another? I'm looking at this line right here. And the thing that I'm noticing about this red line, and notice that this is the origin right here. I know that my numbers got really small in this diagram right here, but there's the origin at 0, 0. And my question is, how would you describe all of the points that are on this line? I just kind of want to identify a couple locations here. That's the point 2, -2. That's the point 1, -2. Or sorry, I can't do my coordinates here this morning. I swapped that's 2, -1. I swapped my x and y. This is 2, 0 right here. This is 2, 1. And this guy right here is 2, 2. So I just identified some of the points on this line. And I'm noticing that they all have an x coordinate of 2. So therefore, the equation of this line is x equals 2. That's literally how we generate that line in the plane, is we just go to, literally, we can go to Desmos and we can do x equals 2. I can pop over here and I can literally just do this, and I can say, hey Desmos, what happens if I do x equals 2 here? When I do x equals 2, oh, what do you know? A vertical line pops up at the x coordinate of 2, right? So that's a really, really natural way for us to define things, and this is using our rectangular coordinates right here. So this is a case in which it is clearly best for us to do our measurement in a rectangular coordinate system, since the sort of binding feature of the infinite number of points on that red line, they all have one thing in common. That's that their horizontal distance from the origin is 2. Since the thing that they all have in common is their horizontal distance from the origin, it's really, really useful for us to use our traditional Cartesian or rectangular coordinates to measure that. What we're going to find today is that there's plenty of shapes in space that aren't just like vertical lines, where it's not necessarily easiest to describe what do all these infinite number of points have in common with one another. It's not necessarily always easiest to do that based on some horizontal or some vertical measurements. So let's look at some other examples here. So again, what I want us to do here, same question as before, is just describe to me all the points on these curves here, and let's see if this leads us to anything useful. So we've got two different curves here. First one on the left is what we call a parabola. The right one is a circle. Both of them are conic sections here. To help us out, I've also tried to plot a couple points on this parabola over here. And so I'm going to go ahead and identify these. 1, 1, 2, 4, 3, 9. Over here we're at negative 3, 9. Here we're at negative 2, 4. And here we're at 1, 1. And I guess I did forget to put a dot right there, but I'll identify that that's at the origin right there. So if I'm kind of just staring at all this list of like the 7 ordered pairs that I've thrown up right there, I'm asking myself, what could I say in general is true about all of these ordered pairs right here? What's the maybe the relationship between the x components and the y components for all of the points that fall on this curve right here? And the thing that I'm noticing is that, and especially I can kind of see it with the 3, 9 point right here compared to the 2, 4. 2, 4 is very, very misleading to me. I just want to point out to you guys, 2 is sort of a math professor's least favorite number here, and that's because 2 plus 2 is 4, 2 times 2 is 4, and 2 squared is 4. And so sometimes when you start with a 2 and end with a 4, it's very not clear how you got there. However, when I see this 3, 9 point right here, that suggests to me it seems like to get from 3 to 9 and to get from 2 to 4, we must have multiplied the number by itself. And I can check that that's true for all the rest here. 1 times 1 is 1. 0 times 0 is 0. Oh, that's a negative right there. Negative 1 times negative 1 is positive 1. Negative 2 times negative 2, positive 4. Negative 3 times negative 3, positive 9. It looks like, seems like all the y values are the square of the x values. Therefore, what is a good descriptor of this line? It should be the line where all the y values are the square of the x value right there, right? So again, by verbally describing the line, that gave me a very clear way to define the relationship between the x and the y values that we're seeing out there. So again, even though this isn't a straight line function, it's not necessarily just about measuring horizontal and vertical distances. There's clearly a well-defined relationship between the amount of horizontal and the amount of vertical. And so even though this isn't some sort of straight line graph, this is still very well described by our rectangular coordinate system with x's and y's, because the nature of the relationship between the x and y coordinates is a relationship between horizontal and vertical measurements, right? For when we're looking at the place that we're at. So that's still a good use of that coordinate system for us. So now we move on to our next shape over here, the circle. And I say to you, how would you describe the set of all, there's an infinite number of points on that circle. How would you describe all of them to me? What's the thing that they all have in common? And I would say here that all of the points on the circle are exactly, and let's see here, this is a 3 right here, 3, negative 3, negative 3. They're all exactly 3 units away from 0, 0. Now, here's my problem with this. How am I going to get this to be some sort of XY relationship right there? Now, it turns out we've seen equations of circles this semester, so I'm hoping you guys remember how we can define this equation here using X and Y coordinates, but it's harder. It's definitely not as easy as the previous two examples that we've done. I feel like I'm able to give a very simple description of of how to identify all the points that are on a circle, but I don't feel like I get that same degree of simplicity when I try to write my equation in terms of X and Y. It's just the set of all points that are distance 3 from the origin. That's a really easy description for me to make right there. I feel like there should be an equivalently easy equation that therefore describes all of those points that are on the circle. So the bottom line is, it's not clear to me at all how I can take my easy description and convert it into an equation if I'm required to use our x, y coordinates. That's kind of my bummer right here. And that's kind of a problem because like circles are very basic shapes. I feel like this is a simple to describe shape. It should have a simple equation associated with it. So we see that some curves are not well described by descriptions of the relationship between the x and y values, but that doesn't mean they're hard to describe. This is an easy to describe shape. I just can't really describe the relationship between the x and y values. That's the hard thing. This is saying it's easy to verbally describe this. It's hard to force this into the XY coordinate box right there. Right? So our typical XY coordinate grid is good for describing locations based on perpendicular distances, right? Horizontal and vertical distances. But that means it's kind of bad for things like circles that aren't defined based on horizontal and vertical distances. So what we're going to do is we're going to define a new measurement system. Rather than XY coordinates, let's define a measurement system that helps us more with things like circles. Right? So we define polar coordinates to help us describe shapes like circles and a bunch of other things as well that are easy to describe, just not easy to describe using our typical XY coordinate system. Right? It's the coordinate system that's our difficulty here, not the description itself. So here's going to be our kind of our two coordinate systems here. To graph an xy point in Cartesian, the Cartesian coordinate system, or in rectangular, we always start at 0, 0 at the origin. We move horizontally by x units, either left or right, and then we move vertically by y units, up or down, and then we have landed at the xy location. Today, we're going to talk about polar coordinates, and we are instead going to be giving a radius and an angle to describe where our points are located. In our polar system here, we refer to the origin. This is just a naming thing right here. It's not really that big a deal. I still generally call it the origin anyway, but its more formal name is the pole, and that's because of the fact that we're doing rotation around it. But the pole is still like our origin. It's still 0, 0. And starting from that pole, we're going to extend by a radius r, which I'm always, notice that my hand motion here wasn't up. I'm always picturing my extending by a radius r being at like our 0-degree angle. Then we rotate by some number of degrees out there to plop us down in space at some location, an r theta location rather than an xy location. So it's just saying we're just describing how to get to the points differently, although we still are going to be able to describe Cartesian points using polar and polar points using Cartesian. This is just a different way to describe how to get to a location. So, and just a quick reminder here, just as you know that every single ordered pair that you've ever seen in your life has always been x comma y, it is also equivalently consistent that we are always going to order our polar ordered pairs as r comma theta right here, our radius first and our angle second. So let's go ahead and take a look at graphing some points in polar here. Now, one of the cool things that I want to do right here is show you that sometimes it's more helpful to use a different grid. And like, how much sense does this make now that we've introduced this idea? This grid over here is very obviously used to be taken advantage of in an XY coordinate system. All those minor grid lines in the background right there, those are all our horizontal and vertical distances that we're traveling. This thing is made very specifically to handle XY coordinate systems. On the other hand, since we're now thinking about extending by a radius and then rotating that radius around by some amount, maybe it's more helpful for us to have more of a radial graph that we're drawing on here. So this is basically like polar graph paper right here. And you can see it has marked off all the radii on here. And then it also has, and I know that you guys can't really see these, but that's like a pi sixth, a pi third, a pi halves, 2 pi thirds. I'm sure that's probably a little blurry on your end right there. But you know what measurements we're looking at here. This thing's just marked off in radians around here with these rotations. So I'm going to go ahead and plot these points on both graphs right here. But the point kind of is to me is that we probably want to be doing this on the second graph rather than the first, because this one's made to handle polar type stuff. This one's made to handle Cartesian type stuff, but we'll do both since it's pretty rare that people have like graph paper that looks like this. But I do also want to point out I did snag this off of Desmos, by the way. So Desmos has this optional, you can switch from this background to this background in Desmos, which is convenient. So let's go ahead and take a look at this here. So if I want to graph the point 3 comma pi fourths, I'm going to first do this in my polar setting over here, and then we'll see why it's a little bit tougher to do it over here. So I'm going to follow the instructions that I saw a minute ago. I'm going to start at the pole, which is here. I'm going to extend by a radius of 3, which is going to take me to here, right? So I'm always going to extend that along this positive x-axis, I sort of still think of it as. Then I'm going to rotate by pi fourths, and that's going to land me right here. Right, there's my pi fourths angle line right here. So this is the pi fourths line right there. So here we are at 3 comma pi fourths. One real quick important thing to notice is my point here is not directly above the number 3 because 3 is not a measurement of my x coordinate. 3 is a measurement of my distance from 0. So what that means to me is that this dashed line has a length of 3 right there. Or I guess I should just say r equals 3 right here. Right, so remember that 3 is not an x measurement, and therefore my point is not above the measurement of 3 on the x-axis. It is 3 units of distance away from the origin or the pole right there. So it's technically the case that that point should be at the exact same location on this graph setting over here. We just have a different background right here. But notice it's much, much harder for me to go ahead and make this, oh man, I want to at least get a 45-degree angle line right here, get my pi fourths on there. It's much, much harder for me to do this because now in this case, using this type of like graphing background, I now have to be able to make the visual judgment for myself as to how far is 3 units. That's a little bit tougher, right? Like I know if I went to here, that would be too much. This is clearly much, much longer than 3 units if my x coordinate alone is 3. But I like don't know anymore, right? And I feel like it's gonna be somewhere like right here. But it's tough to judge this distance. This is my problem of using rectangular grids to graph polar coordinates. And I wrote pi thirds twice now, even though I mean pi fourths, because I'm thinking about 3 being that radius right there. So let me fix this, pi fourths. So that should be our point 3, pi 4. So let's go ahead and do this again. My next point is 1, negative pi. So I'm going to start at my pole, I'm going to extend by 1, and I'm going to rotate by pi. So you should notice this is really like putting us at the point negative 1, or at a radius of negative 1. In a sense right there, but does it really make sense for us to have a radius of negative 1? Now, on this guy, man, I just can't write my ordered pairs here. It's just 1 comma negative pi. Now, you should notice over here in our rectangular grid that I could do a very similar thing. This one's really easy for me to do because since I rotated by pi units right there, I actually did end up making a horizontal or vertical measurement as opposed to this angled measurement that we made in the previous point right there. So it does look like this r theta has an equivalent xy. So I think I might want to make one statement down here. R theta equals 1 negative pi should be the same thing as the xy coordinate of negative 1, 0. So I do want us to kind of start thinking to ourselves, what we want to be able to do in a moment is to say to ourselves, oh, I want my point to be in polar coordinates. Can I convert from my xy coordinates to an r theta coordinate? Or we might want to go the other direction. Can we convert our polar stuff back into Cartesian? So conversions is a pretty important thing that we're looking at here. And here's one way that you can start to think to yourself, like, how would we arrive at these values for xy given these values for r theta? Finally, this last one here is a little bit weird. This is negative 2 pi thirds. And the reason why this one's a little bit weird is because this negative 2 right here is sort of like saying our radius is negative 2. And that kind of doesn't make sense to me because my distances are typically positive distances here. So there's kind of 2 different ways I can go about thinking about this one. One thing I can do for myself is I can, instead of starting out travel on, this is like our 0 radian axis, our 0 degree axis. If you've rotated by 0 degrees, then your point is on this right half of this axis, right? So maybe I'm thinking to myself, let's instead start by going in the other direction over here. This might be my -2 radius is going to the left first instead of going to the right, extending in the opposite direction because we have the opposite of 2. And notice I want to rotate by pi thirds, but pi thirds is a positive number, so I do want to rotate in our positive direction of motion. So what I'm thinking to myself is, starting at this place that I might call a radius of -2 and no angle, I now want to increase my angle by pi thirds. So I might go out to here at pi thirds, right? And now I'm not at pi thirds. That was a sort of a wrong thing of me to say. From where my angle was starting at right here, I added an additional pi thirds of rotation to get to this point here. So I'm thinking that this seems like a good candidate for the -2 comma pi thirds. Now, another way that I could think about this problem is this. Another way I could think about this is I could say, all right, let's ditch the negative for a second. Let's just pretend it's not there. If I did that, then I would go to a radius of 2, and I would extend out to pi thirds, and that would put my point right here. Put an x right there. At that x location is where I've done a radius of 2 and an angle of pi thirds. But now I'd maybe say to myself, oh, and by the way, I actually want you to negate your radius. So rather than extending in the positive direction for my radius out here, we instead extend oppositely through the origin right here. And so you should see that this point right here is in fact okay, it looked like they weren't lining up to me for some reason. This is in fact like a mirror image over the origin in a sense to get to that location right there. So this x would be a +2, positive pi thirds, but instead we sort of, in a sense, you should think of your radius being 2, right? Here's the origin, and here's our radius of 2. I'm going to decrease my radius down to 0, and I'm going to keep decreasing my radius through the origin until it gets to -2. It should just sort of be on that line right there. Finally, another way to think about this might be that our pi thirds angle is in a sense not just a array, but maybe is a whole line through space out here. Right, so maybe this is like my pi thirds line, but very importantly, I drew it extended through the origin here instead of just being in this upper right quadrant. All of our positive radii would end up on the positive leg of that line. All of our negative radii are going to end up on the opposite side over here. So that's why I'm getting over here for our -2 comma pi thirds right there. Right, so all three of these points are graphed in that same location there. Point, 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 and point, point, point. Same, you should see those 3 points are matching, but it's tougher to do this on an XY grid over here because now I have to make like eyeball judgments of like how far is 2 units in this weird angle direction out there, and it's like, to technically get it right, you have to be like multiplying by some square roots and getting some decimals, and now I'm doing 1.73 on a grid that only has a 1 and a 2 on it, and it gets a little tough out there. So going into this coordinate grid system over here might be a little bit more convenient. Let's pop over to Desmos just so I can show you guys this stuff real quick here. Over here in Desmos, the very convenient thing that I can do is over in my settings, I can just switch to, here's my 2 grid choices. You can see a rectilinear grid and a polar grid right here. So I can even go so far as to then, I'm going to plot all 3 points that we just plotted. If you just want to plot individual points in Desmos rather than curves, then up here where you add a new item, you can just add a table of points right here. And the points, ooh, wait, can I add polar points? Let's try this here. I'm actually all of a sudden not sure if it's going to do this for me. Can I make this R1 and theta 1? Is it going to do this for me? And the answer is no. I'm noticing here that apparently Desmos is not down with doing polar. That's really weird. Why are they giving me a polar grid and they don't do individual points here? I'm gonna have to ask the internet about this. I'm noticing here that we clearly have an x value of 3 and a y value. Pi force is like 0.78, and I can see that we're a little bit below the y value of 1. So that's definitely very much an x, y, even though I intended that to be an r theta. So notice that there's a potential for confusion here because we're still using two pieces of information to describe where we are in the plane, but it's not necessarily, if I just gave you an ordered pair 3 comma pi fourths, very technically that could be either x, y, or r theta. And so we always need to be a little bit more clear about what coordinate system we're making our measurements in. So slightly disappointing that it seems like maybe Desmos doesn't support individual points in the plane right here, but it's going to help us out a lot with graphing our curves here coming up in our next video, next section. So look for that. And at least you can see here, oh, that's the wrong thing I have to move right there. At least you can see here Desmos does give us this coordinate grid measured in polar back here, so you can take advantage of this if you want. So again, just up here in settings, you can just switch between which of the grids styles that you want right there. So that's at least good. So let's pop back over and see where we're at here. So another thing that we've just seen here is that maybe there's alternate ways to represent some of these points. And in particular, this guy that had the negative radius right there seemed a little bit odd. It seemed like maybe there's other ways to state that one. So one thing I'd like us to do is to recognize that while our x, y coordinates are all unique, there are multiple ways that we can represent our polar coordinates here. So for example, 3 pi fourths in polar, if that's an r theta ordered pair right there, what are some other ways that we could also describe where this point is located? Well, one thing I think to myself here right away is that I know that one way to get a sort of an equivalent location for an angle is to use a coterminal angle. So one thing that I'm thinking to myself is that I should be able to say something like 3 comma whatever pi fourths is plus 2 pi, right? That location right there should be the exact same location, right? And let's see. Well, I'm just going to leave it in that setting right there. Or it could be 3 comma pi fourths minus 2 pi. That should also land us, that's another coterminal angle. We can go forwards an extra rotation, backwards an extra rotation. Either of those should be fine. What other things could we do here? Well, I'm wondering about this negating the radius. So my question to you would be, if I want my radius to be negative 3, what does my angle have to be? Stop and think about this for a second. And my question to you might be, what's the difference between this point that we indicated with an X right here and this point that we indicated with a dot right here? What's their difference? And in polar, what's their difference? That's the important thing. In polar, they have matching radii of 2. They're both 2 units away from the origin. What's their difference in angle? And it seems like these are a 180-degree angle difference from one another, or pi radians difference from one another. So I'm thinking to myself, I could add pi to 3 fourths to get 5 pi fourths. And now I should be landing at the same spot, right? So 3 comma pi fourths is here. Alternatively, I could have started at negative 3 right here and done 1 full pi plus an additional pi fourths to land at that exact same location. So this is an equivalent representation of this point. All 4 of these ordered pairs are representing the exact same location in space. All right, so again, notice that because our rotation can repeat itself, and because we typically think of radius as always being a positive quantity, but it very technically seems reasonable for us to do negative radii, although we probably should avoid that, and I'm not going to do anything screwy to you guys with negative or radius terms here. It probably should mostly be a positive quantity. One of the distinctions between our rectangular coordinate system xy and our polar coordinate r theta is that in xy coordinate system there's always only one representation of any point in space, but our polar system there are many alternate ways in which you could technically represent that same location in space. So just something to kind of be aware of, that it's technically possible that you and another person might come up with 2 different looking answers for a question, and maybe both of you are right. That's technically possible in polar, that's not technically possible in xy coordinate system. So we should stop for a second and do the important whiny thing that's actually a good academic thing here, is say, who cares? Why are we even talking about this? What does this have to do with anything here? Why should we be learning this? Well, Kind of our deal here is that math gets hard, right? What we want to be able to do is we want to interact with locations in space or curves in space or more generically just objects in their easiest, most natural settings. It seems like there are some unnatural descriptions that we run into, like trying to describe circles, which seem like they're probably really well defined by radius and angle. But using rectangular coordinate system, it's kind of awkward to describe circles, right? So why would we ever talk about circles using x and y? I feel like we should talk about circles using r and theta because it's going to be way easier for us to do, right? So kind of the point here is to say, since math is hard and getting harder, what's important to us is that when we consider some location, curve, object in space, let's define it, let's describe it using the most natural descriptors possible. And just always using x, y for everything is not always going to be the best. Even though you're getting very, very comfortable with one measurement system, using straight lines is a bad way to describe circles, right? So I think that we're going to get some shapes are much easier to define in polar than they are in rectangular. And so maybe that's like a direction that we should go with things. What you guys will eventually find, if those of you are going on and taking some calculus, you'll see it a little bit in Calc 1, but a lot more in Calc 2 and in Calc 3, that there are some scenarios in which we literally don't have a way to apply a calculus process to a curve described in terms of x and y. But then if we convert that equation into being a polar equation instead, polar equations like we're going to talk about in the next video, then suddenly the calculus not only becomes possible, but easy. And so there's going to be several calculus scenarios that we're going to encounter where certain shapes are just straight up not manageable using our typical techniques. But once we convert into polar, everything becomes not just possible, but easy. And so the kind of our philosophy here is to say, don't just pick one coordinate system and stick it out till the end of your life using that one. Let's come up with all the possible coordinate systems that might be best descriptors of certain objects in space, and always use what we think is the most suitable coordinate system to describe that particular shape so that we can manage it most easily here. So this is trying to do ourselves a favor right here for sure. So we'd like to be able to convert between rectangular and polar coordinates so that we can always be in whatever setting is the most appropriate. So what I want to do now is see if we can do this. Let's see if we can convert each of these ordered pairs into the alternate coordinate system. So my question to you is, given that we're at the xy location in space of 3, 1, how would you describe that same location in space in polar instead? And then oppositely, given that we're at the polar location, r theta being 2 pi thirds, how would you describe this location as an xy location instead? Can we convert system we convert information from one measurement system to the other measurement system? So let's draw a picture and see if we can make this happen here. So when I'm thinking about the xy coordinate of 3, 1, I know that this means I go 3 units to the right and 1 unit up. And so as I drew earlier, I feel like I'm picturing to myself that I've got this horizontal motion and this vertical motion. I know you can't really see it right here. I've just drawn like a red line right here and a red line right there, those two red lines. And it feels to me like the thing that I'm sort of doing right there is drawing like, I don't know, two perpendicular lines coming together to form a 90-degree angle right there. What I know I'm about to do is I want to be able to identify what was the angle that was opened up at here and what is the distance from the origin to that point. Well, that distance from the origin to the point seems to me to be completing this diagram of like a right triangle right here, right? So it seems like here's my unknown radius, and it seems like here's my known x and y coordinates. This is a 3 and this is a 1 because we're sitting here at 0, 0. And we're sitting here at 3, 1. What we want to know is, what is this theta and what is this radius right here? So my question to you is, given that we have found ourselves in a right triangle, can we solve for these components r and theta? So let's do the harder one first. I think that r is easy because we're in a right triangle. We're going to use the Pythagorean theorem to solve for r. Let's think about theta here first. Just because I don't know, I want to do the harder one first. I want to say, because what I don't want to do is I don't want to use our r piece of information to find theta. If your job was just to find the angle right now, knowing those numbers 1 and 3, my question to you is, what trig function should I use right now to help me find theta? Answer that. The answer you should be saying here is tangent, because opposite of theta is 1, adjacent to theta is 3, and so it seems like I can make this statement here that tangent of theta is opposite over adjacent. And therefore, I think it's pretty reasonable that we just apply an inverse tangent to both sides. And I should be able to go and get an angle out from this guy right here. Let me give myself just a smidge more room right there. So let's go pop over to Desmos and ask it what tangent inverse of 1/3 is. So I'm looking for my tan inverse of 1/3. Sorry, my screens are perfectly overlapping each other here. I'm looking for tangent inverse of 1/3. I'm remembering that Desmos has probably got me in radian mode right now. Generally, when I'm describing triangles, I kind of like them to be in degree mode, I think. So it's easier for me to like think about the whole like 90 degree, 180 degree business that we know about with triangles, with right triangles. So it seems like Desmos is telling me we're getting like an 18.43 degrees for that angle right there, 18.43 degrees. So I'm going to come back over to Word, 18.43. So we got one of our two pieces of information. And by the way, all of our polar coordinates that we've seen so far have been in radians. But just like with everything, we use a little bit of radians, a little bit of degrees. It just depends on the situation. So we've managed to find our angle. Let's go ahead and see if we can find our radius right here. For this statement, I know I can use a little Pythagorean theorem. 1 squared plus 3 squared equals r squared. That's going to give me 1 plus 9 equals r squared. So it seems like r is going to be the square root of 10, right? 1 plus 9 is 10. And I'm going to take the square root on both sides. So it seems like what we've ended up finding here is we have found both the radius and the angle at which you need to travel to arrive at the xy coordinate of 3, 1. And so I think I can say that this is equal to the r theta point of r is square root of 10. Theta is 18.43 degrees. Right? So there's my final answer for this one. I've converted the xy information into r theta information, and that's because I recognize that a right triangle will help me kind of swap out my pieces of information. Right? Now for our second one right here, it seems like we're interested in finding r theta being 2 comma pi thirds. So I'm going to go a radius of 2. There's my 1, 2. But I want to rotate this guy around by pi thirds right there. So I'm thinking to myself, pi thirds feels to me like, about like this angle right there. That seems like a pi thirds angle to me right there. So I know that we're at an angle of pi thirds, and I know that we have a radius of 2. And it seems to me like what we're interested in finding is we're interested in identifying how far right do I need to go to make this point happen, and how far up and down do I need to go to get us to that point right there. So once again, there's a right triangle in space that's helping describe to us this relationship between our r and theta information and our x and y information. So in this problem here, we were given that our radius is 2. We were given that the angle is pi thirds, and what we don't know is what's x and what's y. So now the next question is, what math can we do given this right triangle to solve for x and to solve for y? So I'm going to again ask the same question as I asked last time, which is, if I want to solve for x right now, what trig function should I use to solve for x? What trig statement can I make to solve for x? There should be a small little trig equation that we can write that's going to help us solve for x. So stop and think about that for yourself for 1 second. I will take my coffee sip and then we'll write an equation for x. So the angle that I know in this right triangle is pi thirds. So I want to make a statement relative to this angle here. I'm seeing that relative to pi thirds, x is adjacent and 2 is hypotenuse. So what trig function is associated with adjacent and hypotenuse? And we know that cosine is the adjacent over the hypotenuse. So I'm thinking to myself, cosine of pi thirds is adjacent over hypotenuse. Right? So if I wanted to solve for x, I'm noticing that I do know the value of cosine of pi thirds right here, but I'm thinking to myself, maybe this is some crappy decimal that I don't want to evaluate this yet. I'm noticing that to solve for x, all I'm going to do is multiply both sides by 2. Now I can evaluate this totally. I've solved for x already, right? This is my exact answer right there. And what is cosine of pi thirds? I'm noticing cosine measures our horizontal distance right there. I'm noticing that this is the shorter of the two legs, and I remember that all my 30s and all my 60s give me the options of 1/2 or root 3 over 2. It looks like the x-coordinate is the smaller of the two choices there, so I'm thinking that cosine of pi thirds is 1/2. So it seems like our x-coordinate should just be 1. All right. Now, what do I want to do for y? Well, my y stuff is going to be super duper similar. The only real difference here is that, again, I still only know my angle pi thirds and my hypotenuse of 2. It seems like y is opposite of pi thirds. So opposite and hypotenuse tells me use sine instead of cosine. So I'm thinking that I can say that the sine of pi thirds is going to be y over 2. And once again, I could do my algebra first here, multiply by 2 on both sides. And now I can say to myself, all right, and what is sine of pi thirds? Well, again, I know that I'm picking between 1/2 and root 3 over 2 for all my pi thirds and pi sixes, or all my 30s and all my 60s. I can see here that the y component is the larger of the two choices right here. So I'm going to choose the root 3 over 2. So y is 2 times root 3 over 2. And that's just going to be root 3 because the 2 and the 2 cancel right there. So it looks like we've found all the information that we need to relate our x and our y coordinates to our r and our theta coordinates. So it seems to me like we could now rewrite this as the xy ordered pair of 1 comma root 3. So there we go. I converted my r theta information into xy information right there. So this is good right here. And I feel like I want to get a little divider line for this problem right there. There we go. So notice the important thing here is that to convert between our two measurement systems here, our xy and our r theta stuff, this literally just boils down to just having one right triangle. And we're masters of right triangles by now. So the math here is nothing that you haven't seen before. We're just using it for a slightly different purpose now. So it seems like both conversions were dependent on a right triangle. Let's find general conversion. Let's find general formulas that we can use rather than having to think through all this, that we can just do to relate our two coordinate systems. And very, very importantly, this all boils down to just drawing a basic right triangle. So what I'm going to do is I'm just going to draw a generic triangle just like I drew these generic triangles up here. The only difference is I'm going to leave all of the unknowns unknown, right? We don't know any of the numbers. So our four terms are x, y, r, and theta, and I'm going to place them on their appropriate locations on the right triangle. So this is my x distance, this is my y distance, this is what I'm calling my radius, it's really my hypotenuse, and this is our angle through which we rotated to arrive at that location, right? So this is always going to be 0, 0, and this is going to be our point that we can either describe as x comma y or as r comma theta, right? That's it doesn't matter because I've in this diagram I know all four pieces, or I don't know all four pieces, either way that you want to think about that there. So the point is, how can I make my general formulas here? Well, literally, I just want to basically state the general versions of these four computations that we just did right here. So for the first one, or I guess we should say, if we know x comma y. So notice that in our first example, we knew the x and the y coordinate. We didn't know the angle or the radius right here. So what were the computations that we did to get the angle and the radius? Well, it's always going to be the case that knowing x and y is going to lead you to a tangent type equation right here. So what did we do to get our angle for theta right here? We said that we could say, well, it's always going to be the case that the tangent of theta, and looking over here, tangent of theta is opposite over adjacent. It's always going to be y over x. And so it's always going to be then appropriate for us to say theta equals the tangent inverse of y over x. We're going to end up seeing that this one is going to be the one that's going to occasionally do slightly weird things to us here out of the four computations that we do, but we'll see that when we get to an example with it. But there's one of our relationships right there. So if we know xy, we can do tangent of theta equals y over x. We can also make this statement right here that x squared plus y squared equals r squared, or I'll write it as r squared equals x squared plus y squared. This is our Pythagorean theorem. And all we got to do is take a square root on both sides. So it seems like our r value is always going to be the square root of x squared plus y squared. So here are two of our primary conversions. This is how we go from xy into r theta. If you know your x and y coordinates, you can compute your r and theta coordinates instead. Now, alternatively, if we know r and theta and we want to convert to xy, what do? Well, that's just these examples right here. And you should notice that both these look very similar to one another. It's always going to be this case that we can say that the cosine of theta is going to be adjacent over hypotenuse. We can always start with our cosine of theta is our adjacent over hypotenuse. And all I'm going to do, since I want to know what is x, is I'm going to multiply by r. So it looks like x equals r cosine theta. And very, very similarly, I could instead take the sine of theta. That's going to give me y over r. And I can multiply both sides by r. And I'm going to find that y equals r sine theta. And now we have our two conversions that get us out of polar and into rectangular. So these are just the general formats of the four computations that we did up above right here. These get the underline if the ones on the left got the underline right there. And so these are general conversions. And by the way, these, oh, I know I'm falling off my edge a smidge right there. Can I slide over? There you go. So in general, what I would say to you guys is this diagram is the thing that you actually need to remember. When people, and this is one of those things like when I'm tutoring and people are like, oh shoot, I forgot how to convert with polar. I give them, this is one of those few ones where I generally consider myself a pretty nice, friendly, approachable guy. This is one where I just give people a dirty look and I just come over and I just draw this picture and I frown at them and I walk away. This picture is all I remember. These formulas are not the thing that I remember. Knowing this picture, you should always be able to take in any two pieces of information and solve for a third piece of information on this triangle here. In particular, theta and r are always a pair, and x and y are always a pair. And so just this generic picture here should be enough for you to come up with these four formulas on your own. You've literally done 100% of this math already before. 100% of it. We just haven't stated these as general conversions before in the same sense as we're seeing them now today. All right, so just this generic triangle down here, nothing special about it whatsoever. This is my guide for understanding how to convert between polar and Cartesian coordinates right here. And again, when I'm in like Calc 2 class and people are like, oh, I forgot how to convert to polar, I just give them a mean look and I just draw this picture and I say nothing and I walk away and I'm like, that should be enough for you right there. So this diagram, that's your key right there. Just know you're a generic right triangle. So let's go ahead. Let's go ahead and take a look at some kind of usage of these relationships, and then we'll do some more conversions, but we'll do them really fast right here. So one usage of this relationship is to say, let's come back to this circle diagram now and see. And I want to ask you, like, how could you describe this circle to me now? Well, remember that we said that this circle is the set of all points that are 2 units away from the origin. What I want to remind you of is the very, very, very first graph we looked at today. First graph we looked at today, I said, hey, describe all these points to me. And you said, oh, they're all the ones that have an x value of 2. And so what did we call the equation? X is 2. It's literally the sentence x is 2 is the descriptor of this line. Now I come down here and I say to you, hey, describe all these points to me. And you say to me, oh, they're all distance 2 from the origin. They all have a radius of 2. Points all have a radius of 2. So what do you think the equation should be? Well, that's nice and easy right there. And the cool thing is that Desmos agrees with us. If we come over here and check this guy out in Desmos, now I had some issues with plotting a single point in Desmos earlier, but equations it's cool with. Boom, r equals 2. It just gives me the circle right there. This is the set of all points that have a radius 2 distance from the origin right here. That is a really nice, clean, easy descriptor of a circle, right? So this literally is the equation of a circle. Is r equals some constant number. And that says, yeah, your radius is constant. Notice here that theta never crops up as the discussion. Just like above, y never cropped up for the discussion. Up above with that vertical line, we would say, well, there is no restriction on y. Y can be anything it wants as long as your x-coordinate's 2. And that's why the equation only talked about x. Here I'm saying, oh, there's no restriction on the angle. The angle can be anything it wants as long as the point has a radius of 2. There is no restriction on theta, so it didn't get included in the equation here, right? Um, so, so my instruction here, though, says determine the equation for the following graph in both polar and rectangular. So this is my polar equation of this graph right here. And so now what I'm thinking to myself is, can I convert this into rectangular? And the answer is yes. And the reason the answer is yes is because I know a way to convert r information into x and y information. Coming up above here, we learned that r is the square root of x squared plus y squared. And I generally don't like writing my equations with square roots in them if I can avoid it. So in general, we typically just square both sides. And this is our Cartesian description of the same circle right there. X squared plus y squared equals 4. Or maybe we want to write this as x squared plus y squared equals 2 squared. It's generally the case that the general formula for a circle is the x squared plus y squared equals whatever the radius of the circle is squared. So sometimes this helps me remember that this is a radius 2 circle, not a radius 4 circle right there. But we should justify this real quick. Come over here and do our x squared plus y squared equals 4. And you should notice here, maybe I can swap out for some better colors here, that these are clearly overlapping one another, and you can tell because as I turn one off or on, it's changing colors because the orange one's just getting put down on top of the blue one right there. So you can see that these are both equivalent descriptions. These two equations are literally the same as one another. One is just using a different coordinate system than the other, so they look different, but they're identical descriptors. They're describing the same infinite set of points that are out there, right? And again, the whole takeaway from this is one of these equations is simple, r equals 2. One of them is complicated, x squared plus y squared equals 4, or 2 squared over there. This is more complicated because this is a less natural type of setting to describe this in. This is a description of relationships between horizontal and vertical distances, but that's not a good descriptor of a circle, especially when we consider that angles and radii are one of our options. Obviously, it makes sense to describe a circle based on a radius rather than by some x and y coordinate relationships out there. So complicated equation because this is not a good setting. Simple equation because this is a very good setting for polar coordinates right there. Right? So same equations right there. So let's do some quick ones right here. See, there's not a lot of room. And in fact, I think here is a perfect example of where you should stop for a second and pause this video right now and do all 4 of these. Because why wouldn't you just see if you can get these right here? So see if you can remember the formulas on your own without looking back, and see if you can do these 4 conversions right here. These top 2 are in polar, convert them into rectangular. These bottom 2 are in rectangular xy coordinates, convert them into polar. So pause right now and do that. And I'll do it right now. Now that you're unpaused, I'm recognizing here, and again, I kind of like to say to myself, this is my r and this is my theta. So I know that x equals r cos theta. So x is going to be equal to 6 cosine pi sixths. That is going to be 6 times root 3 over 2. And therefore, I think this x coordinate, 6 is going to cancel with a little bit of that 2 down there. So I'm going to get a 3 root 3. Similarly, my y coordinate here is going to be 6, sorry, I'll write my whole formula here since I'm doing my earlier examples. Y is r sine theta. And again, realize that these formulas totally match your intuition. We know that the cosine function helps measure our left-right location on the unit circle. Well, all we're doing is we are getting our x information using the cosine function. We are getting our height information. The sine function is tied to our y value right there. So this all like agrees with my intuition about what job these trig functions are doing. 6 sine pi sixths. This is going to be 6 times 1/2, and that'll give me 3. And so I think that I can say that this is the xy point of 3 root 3, comma 3. I think that's my final answer right there. All right, for the next one here. Notice I've got this awkward thing of this radius of 4. I don't think that's going to bother me too much here. My x is going to be r cos theta. So that's going to be my x being negative 4 times the cosine of pi fourths. And that's going to give me negative 4 times root 2 over 2. And that's going to give me negative 2 root 2. For my y coordinate, now I know that pi fourths is one of those 45-degree angles where typically our x and our y coordinates are identical to one another. They maybe differ by a sign, and that's about it, right? So I'm noticing here it should be r sine theta. That's going to be negative 4 sine theta. That's going to be, that's going to be negative 4 sine pi fourths. And it looks like this is the exact same place right here, negative 2 root 2. It's not surprising to me at all because I know that my pi fourths is, my 45 degrees is that are out there, they always have matching x and y coordinates there, and we did in fact get that. Matching x or y coordinates, give or take a plus or minus. Here they were just straight up the same because we're in the first quadrant, so positive x value, positive y value right there. So it looks like we're at negative 2 root 2, comma, negative 2 root 2. Now, I just did this with my arms, the first quadrant out there, but because we had a negative radius, we were actually at the version that was down here in the third quadrant by going in the negative direction on that line. So in the third quadrant, we know that our xy points always have those two negative values right there. So let's go ahead and do the bottom ones now. We convert it into x and y. These ones are kind of extra easy because the x and the y conversion are kind of like the same conversion as one another. The polar ones are slightly more exciting than that because they're two different equations that we get for these guys. So I'm remembering here that my, and so by the way, I want to make sure I don't kind of like screw this up right here. I know that this point 2, 2, that this is an xy pair. And I'm thinking to myself that this should be 2, negative 2. So I'm picturing that we're going to be down here. In fact, I can already see that we should be getting an angle of something like negative pi fourths or something for this guy. Or maybe that we should be getting like 7 pi fourths or something like that. I know where we're going to be. So I'm not, notice how outrageously simple my graph is. I'm not trying to go crazy with any graph drawing right here. But this is going to be like my sanity check, right? Making sure I'm double checking that I'm not doing anything crazy here. So my first equation I'm thinking of is that theta equals tangent inverse of y over x. Okay, I'll write the equation, then I'll throw the numbers in. Theta equals tan inverse of y over x. That means that theta is tan inverse of negative 2 over 2. And that means it's time for me to go to my calculator and ask it, what am I going to get for that? So let's go and ask our calculator. Tangent inverse. And I'm going to just leave it the way that it was, negative 2 over 2. And unsurprisingly, I got that negative 45 degrees exactly like I knew to expect right here. So that's good. That totally matches the picture that I drew a second ago. That point has been rotated negative 45 degrees from our starting spot right there. So I'm okay with that being listed as negative 45 degrees. I don't need to do anything with that. Let's compute our r value here. R should be the square root of x squared plus y squared. So r here is going to be the square root of 2 squared plus negative 2 squared. The one thing to watch out for here is the same thing to watch out for always with the Pythagorean theorem. Negative 2 squared is 4, just like positive 2 squared. It is always, always, always the case that you're going to add two positive numbers underneath here, because every time you square a number, it becomes positive. So this looks to me like it's the square root of 4 plus 4. And so it looks like r is going to be the square root of 8. So I feel pretty good that my general answer here should be r theta equals root 8, comma, negative 45 degrees. certainly the case that you could have written this angle in radians, or we could have done the positive angle. So like positive 315 degrees also would have landed us at that same location. That would have been just as good as well. So, you kind of get some choices out there. So let's do one other example here. And by the way, this is the important one right here where I'm going to highlight something special. So this is our XY pair right here. This is my x comma y is this guy. As I should do, since I'm a responsible mathematician, I'm always going to draw myself the tiniest, simplest little picture to make sure that I don't do anything crazy. And -1, negative root 3 says go -1, a little bit farther in the y direction is the x direction. So -1, negative root 3. I think that this is where my point is located right there. And I'm just going to use that as to make sure I don't do anything crazy here, right? So let's go ahead and do our theta equals tan inverse of y over x. This is going to be theta equals tan inverse negative root 3 over -1. And notice that really this is the same thing as theta is tan inverse of just positive root 3, right? So I want to say, hey, what is it that we tan inverse of square root of 3? In fact, I think this is one of our known values, isn't it? Yeah, it's 60 degrees. And so now I give you the crazy eyes and I say, why am I giving you the crazy eyes right now? Does that point really look like it's at an angle of 60 degrees to you? Especially knowing that we're guaranteed to get a positive number out from our radius computation over here. Now, here's the thing that I know. The thing that I know is that tangent inverse is always going to output an angle for me on the right half of the unit circle. Always. That is the output that you're always going to get from going to a calculator and asking it to do inverse tangent. The reason that this is going to be a kind of a weird discrepancy right here is that notice that this function, when we do tangent inverse of the ratio of y over x, you should notice that these two negatives are canceling right here. So tangent inverse can't distinguish between the points -1, negative root 3 from +1, positive root 3, because when we take the ratio of both those, you get the same number, positive square root of 3, right? So that says to me that it can't distinguish between first and third quadrant. And very similarly, if you have a positive y and a negative x, that's going to look just the same as having a negative y and a positive x, because who cares where the negative is in a fraction? If you stick the negative on the top of a fraction, that's the same as you sticking the negative on the bottom of a fraction. But in your mind, in this case, that's referencing two different points, maybe a second quadrant and a fourth quadrant point, but the tangent inverse function can't tell the difference between those two. It's just got a negative in there if it's second and fourth quadrant. It's just either positive, positive, or negative, negative, and the negatives cancel to give you back positive again. And so it just referenced for us a first quadrant angle, but we know that we're in the third quadrant. So what are we going to do to get to our actual correct value right here? Is it seems like we need to add 180 degrees to land at our correct location right there. It gave us sort of that rotational mirror image right here. So it should be, and so here's what I'm going to do for myself. So I'm going to say, so tan inverse always outputs an angle in quadrant 1 or quadrant 4. If we are in quadrant 2 or quadrant 3, and notice we're in quadrant 3, it's a quadrant 3 angle right there, need to add or subtract 180 degrees or pi radians from the calculator output. So this is one of those ones where you have to do a smidge of actually paying attention when you do your convert into polar and solve for theta, right? It's always going to be the case that 50% of all of the angles that you could land at are actually going to mislead you according to your calculator output, because your calculator will only ever give you angles in the first or fourth quadrant for tangent inverse. So if you know that it's in the second or third quadrant, which we can so easily tell by just plotting it super quickly, then you know that you're going to have to add 180 to get to your correct theta right here. So what that tells me is I'm going to add 180 to this. I'm going to get 240 degrees as my appropriate location. And that makes sense for this angle over here, that we went 180 to get here and then 60 more from the negative y-axis to get all the way around to where our point was at. So we found our more appropriate theta here. So I want to add 180 to get to 240. So I'm saying that's the thing that can't be right, is the 60, but we add 182 to get to 240. That is going to be correct right there. And that's just one of those very basic limitations of the inverse tangent function and all of our inverse trig functions, that we know that they're stuck only giving us outputs in one little span, whereas we might want to see other outputs. We have to manually make that adjustment here. So our other bit of computation here, not bad. R equals the square root of x squared plus y squared. I'm going to get that my R equals the square root of -1 squared plus negative square root of 3 squared. And that's going to give me R being the square root of 1 plus 3, which is the square root of 4, which is really just 2. So we're at a distance of 2 from the origin exactly, but at an angle of 240 degrees. So it looks like I can say that my final answer here is r comma theta equals 240 degrees. Right? And again, inverse tangent is the one out of the 4 conversions that we do. The only thing that's going to do screwy things to you is that inverse tangent is only going to be right half the time. And the other half the time, you need to either add or subtract 180 degrees or pi radians to get to your correct location. So you've got to watch out for the inverse tangent. The other 3 conversions, straightforward. So as our last problem for the day, I want to look a little bit into what we're going to be doing in 9.2, polar equations in graphs. I want to transform this equation from polar into rectangular, and then I want to graph that equation right here. So this one's going to be a little bit trickier. This one's going to involve some algebra steps that some of you might not be familiar with if you haven't taken college algebra, but I'll talk you through the basics of these guys right here. So here's what I'm seeing. My instruction here is to convert from polar into rectangular. So what that means is I'm trying to find some ways to write things as x and y. So I'm thinking to convert to x and y, want terms like our conversion terms, I'm seeing things like r squared equals x squared plus y squared, or r cos theta equals x, or r sine theta equals y. So what I'm not seeing is I'm not seeing any r squared, I'm not seeing any r cos theta, I'm not seeing any r sine theta. And so I'm asking myself, what algebraic operation could I do to this thing right now to forcibly create these things? And notice I did leave off our theta equals tangent inverse of y over x. That one seems wildly unlikely to me to be cropping up in this equation over here, so that's why I kind of skipped this one. All of these look like things that were nearby, right? That we like almost have something that looks like that. I have an r instead of an r squared. I have a sine theta instead of an r sine theta. And so notice in both of these cases, I have r instead of r squared. I have sine theta instead of r sine theta. It seems like on both sides of the equal sign, I could get stuff that looks more like our xy parts here if I multiplied this whole thing by r. So I'm going to go ahead and multiply both sides by r. And the reason I'm multiplying by r is just because I want to make terms that look like one of my conversions back and forth. Now that I've done this, I actually see two different substitutions that I can make that are going to get me into xy land out of r theta land. One, I can see that I have r squared, which seems to me to be able to be rewritten as x squared plus y squared. Two, I have an r sine theta sitting right there, and r sine theta is exactly just y. So it looks like I've got a 4y right here instead. So we've done our first step. I have converted the polar equation into rectangular. We're now in terms of x and y instead of in terms of r and theta. And I got there just by using my conversions, but I had to do a little smidge of algebra to get me there. Now it wants me to graph it. This one's going to be a little bit tougher, so stick with me on this one. This is a little bit of a harder algebra step. Even my people that have taken college algebra often struggle with this one a smidge right here. What I want to do is I want to get this thing into a general form. When I see x squared plus y squared, this is screaming circle to me, but clearly it's going to have some weird adjustment to the y components because we have this extra 4y right there. So here's what I'm going to do. I'm going to move over all my terms to the other side. And what I really want here is I don't just want a y squared alone. I want all of my y terms collectively squared. So here's what I'm going to do for myself. I'm going to recognize that y squared minus 4y almost looks like something that I would get out of squaring a binomial if there was another constant term plus some special number over here on the other side. What we're going to see, we're going to talk about this a little bit more in the coming weeks here, is that if I were to go ahead and, for example, add 4 to both sides of the equation. Right? I added 4 on the left and I added 4 on the right. That now these terms right here are what we refer to as a perfect square trinomial. These are really just a binomial squared. So notice that when we do things like x plus 1 squared, if we square this out, we get this guy here, x plus 2 squared. We get x squared plus 4x plus 4. This is exactly our situation right here. So we're about to use that guy. If we did x plus 3 squared, we actually get x squared plus 6x plus 9. So notice here that for all of anytime that we have our first two terms, x squared plus some number of x, what we could do is we could always figure out what's the extra constant we need on the end to be able to rewrite it as a completed square, a binomial collectively squared. In this case here, you should notice the only difference between what I've got on my middle line over here is that there's actually a minus right there. So this is going to condense down to x squared plus y minus 2 squared equals 4. This is a circle of radius 2, right? 2 because 4 is really 2 squared. But notice that I have this y minus 2 instead of just y squared. It's y minus 2 squared. You should notice that that means that you need to plug in 2 to make this term be 0, whereas in a regular old circle, x squared plus y squared equals r squared, you'd need to plug in 0 to make it 0. So that's going to shift us up by 2. And so where that's going to then lead us then for our graph is that we have a circle of radius 2 that's been shifted up 2. So instead of radius 2 sitting at the origin, it's now sitting on the x-axis. This is at a height of 4 up here because this is at a height of 2 right there. So this is my circle of radius 2 shifted up 2 units. So as our final thing for the day, and it depends on some algebraic skills to make it happen, right? I think this algebra here is a little bit tougher. This conversion into rectangular, you guys should be able to do. This little bit of algebra right here and recognizing this general form of a circle, a little bit tougher. But this really represents our transition to the next section. Let's just real quick verify that I'm not lying to you, and then we'll go ahead and call it a video right here. Our claim is that r equals 4 sine theta equals a circle of radius 2 shifted up 2 units. That's not obvious at all from this equation, but it's a really simple equation. It's a lot simpler than this final one that we wrote down here in rectangular. So let's go ahead and see it over here in Desmos. R equals 4 sine theta, and we're doing r equals 4 sine, and I just type out the word theta, and what do you know? We get a circle of radius 2 shifted up 2 units from the origin where it was originally sitting. This is equivalent to our x squared plus y minus 2 squared equals 4. And you can see, again, this is clearly the same graph. They're graphed right on top of each other right there. So that's how I know that my algebraic manipulations must have been good. Our polar equation exactly matches our Cartesian equation right there. So that's going to wrap it up for us here today for polar coordinates. You guys can see that we're going to talk more about these polar equations and their graphs in the next section, right? So this example right here, I'm guessing that this was probably a little bit challenging right here. That's cool because our entire next section is going to be thinking more about these things. The big thing that I will say to you is this is one of these big time moments where you should stop for a minute and just say out loud to yourself, man, I'm glad I'm taking this class in 2021 and I have Desmos to help me. Just picture trying to figure this stuff out 50 years ago without having any nice graphing calculator. Next section 9.2, we're going to lean on Desmos heavily to generate lots of pictures that would be very challenging for us to create by hand. So get comfortable with Desmos. It is your best friend, especially for section 9.2. So I'll see you for the 9.2 video when I see you in the 9.2 video. Have a good one.